challenging. You know, the math in it's a little bit challenging. We've got some trig, cosine, sine, tangent, some of that stuff. You know, and the note packet's going to take us a few days to get through. So, be real careful. Write down things, ask questions if you have them. Okay, so let's go to the notes. Ready, break.
Now, let's start off with these two types of early measurements that we have in science. This first type is called a scalar. A scalar is just a measurement with a number. So, for example, I might say, hey, how far did you run? I ran 10 miles. Okay, that's a distance idea. Okay, I might say to you, hey, how hot is it in the room? It's 70 degrees Fahrenheit. Temperature, that's a scalar. Hey, how fast did you drive? I drove 70 miles an hour. That's speed. That's a scalar. A vector, on the other hand, is a measurement with a direction. Okay, now this measurement is also called the magnitude of the vector. So one of the things we just studied was gravity, free fall. Now, we said that gravity acts at 9.8 meters per second downward. Gravity's pulling things downward to the earth. We could also say negative 9.8 meters per second. The negative sign, or the word downward, tells us a direction. The 9.8 part is called the magnitude. The negative sign, or the word downward, is the direction. We need both of these, the number plus the direction, to really explain this concept called free fall. That's an acceleration. Acceleration then is a vector. It needs a number and a direction. Velocity is also a vector. Velocity, we might say, okay, I drove at 70 miles per hour east of Lawrence. Okay, the east is the direction. The 70 miles per hour is the magnitude. Displacement, that's a vector. Maybe I ran 10 miles north of my house. Okay, that's a direction tied into that measurement. So there's a lot of things in physics that require a direction to really understand. And that concept of a magnitude or a number with a direction, that's called a vector. Other things, though, do not require a direction. That idea is called a scalar. It's just a number. Okay? Now, we have acceleration, we have velocity, we have displacements. Those are just three examples. But what we can do is we can add vectors up to get what's called the net or the resultant vector. Let me give you an example. We often show vectors with arrows. Sometimes our vectors are what are called collinear. They're acting along the same grid. So maybe we've got then this plane, and we can show then vectors by drawing arrows. Maybe the engine of the airplane can propel the plane at 200 miles per hour. That's due to the engine of the airplane. Well, maybe we also have a tailwind. This tailwind is pushing the plane maybe 50 miles per hour. Now notice that these two vectors are aligned along the same grid. They're both in the same direction. Both are propelling the plane north or upward. So what we can do is take the two and we can say, well, 200 plus 50 is really a vector that's 250 miles per hour. Both of these are velocity ideas, so we can add them up. That's called the resultant. It results, this is what results from these two separate sort of velocities. We can add them up. They're both collinear. They're along the same grid. let's now turn the page. You know, this idea with this headwind really gets us into our next whole topic, and that's what we call then the grid. And really, you know, we really have to have a way of expressing direction. And the conventions or our grid can really help us. So, you know, we generally start like it at some sort of an origin point, and to the right is considered positive. Now in compass headings, that would be east. And then to the left, we consider negative. And again, that would be west in compass headings. We can also then create a grid that's vertical, and we would have north and south. Again, we'd have positive, and then we'd have negative. So things that are going downward or southward are considered negative. That's why we really said then that this upward velocity here, 200, we have 200 minus 50, because we call this downward vector a negative. And we're really then subtracting. Well, we could put these two grids kind of together and then form then what's called a two-dimensional sort of grid. And that then has a vertical and a horizontal grid put together. This is our system or our quadrants. We've got first, second, third, and fourth. So again, we can talk about this being east, north, west, and south. Positive, positive, positive to the right, positive upward, negative to the left, negative downward. Well, we can also talk about 0 degrees, 90 degrees, 180 degrees, 270 degrees. So we could put a vector in to this two-dimensional grid, and we could say, well, maybe my plane was traveling at, you know, maybe 300 miles per hour at a theta or an angle of maybe 60 degrees. Okay, that would be a first quadrant idea. And we could say then that this 60 degrees, we could say that this was 60 degrees north of east. So if you're looking east, you would rotate your body 60 degrees towards the north, and you could then point along that vector that the plane was moving. So we can call that 60 degrees north of east. And we'll be working a lot in the next few days with compass headings and with this grid. So one number line really means we have a one-dimensional problem. We could go, you know, horizontal, we could go vertical. We put these together, and now we have what's called a two-dimensional or a 2D, two-dimensional type of motion. Okay, I think we're ready for page 3. Okay, so we've been talking really about kind of collinear, but let's actually kind of continue the discussion of this two-dimensional type of problem. Let's say we have a plane that moves north at 150 miles per hour. And now, instead of the wind being either a tail or a headwind, we have this, what's called a crosswind, that's pushing the plane. In this case, this wind is from due west. So this plane is getting pushed north by its engine, and it's getting pushed east because the wind is from the due west. So the plane's getting pushed east because of the wind. And we'd like to really figure out, well, what's the ensuing type of motion that the plane will have? These problems aren't hard, but they do involve a little bit of trig, okay? So this would represent 150 miles per hour. This is a vector that's from the engine, and it's pushing the plane north. And let me get another color here. And then what we do with the other vector is we also started on the origin, and that's that 50 mile per hour wind. So here's kind of what we do. We put the vectors on the grid, and then we kind of can make a box here. Do you see? We've made this little rectangle. And what I can do is, just to kind of give me a little bit more room to work, let me kind of take these and put it down here. what we've done is, or what we can do here is we can create this kind of box, and we'll then take and find the vector from the origin up to this intersection of this box. And you see then what we've created really is a triangle. And the triangle we want is the one really attached to the grid. So this is kind of the triangle we want right there. And what we've got then is a right triangle. See, there's your theta. There's your right triangle here. And we always measure the angles from the x-axis. There's your x-axis. See, there's your x-axis. And the hypotenuse would really represent the true motion of the airplane. And that hypotenuse can be found with Pythagorean theorem. See, it says Pythagorean theorem. So we know that this leg, this vertical leg, was 150. And this adjacent leg, or the horizontal leg, was the 50 mile per hour wind. So we can use the Pythagorean theorem. We can take 50 squared plus 150 squared, and we can take the square root of that, and we're going to call this again the resultant, or that's given the symbol R. So that's a good thing to do on your calculator, right? You can take 50 squared, 150 squared, get the square root, and I'll kind of let you do that. Did you do it? Okay, I get about 158 or so. So what we're saying then is that the plane, how fast is the plane traveling? Well, the plane is traveling at 158 miles per hour. Okay? Notice we just can't add 150 and 50, or we can't subtract the two, or we can't add them, because they're not collinear. They're perpendicular vectors. So we have to use Pythagorean theorem and trig to actually get then this resultant. Now, the other thing is important really is the direction. Where's the plane going? What's the theta? It's not traveling north, it's not traveling east, it's traveling a combination of the two. Well, there's a little secret here to get the direction. So we know this 150 is what's called the opposite leg, and the 50 is called the adjacent leg. And we know then the tangent of that angle, would be the opposite over the adjacent. Or that's 150 over 50. So there's kind of a trick on doing this in your calculator. First off, if you've got a graphing calculator, you want to check the mode. All right? So you want to click the mode button and make sure you're in degrees. All right? That way this will work for you. So what you'll do is you hit second tangent. Okay, do you see that? Second tangent. And this actually will then help us to figure out the angle. So we'll type in 150 divided by 50. We'll close my parentheses and then I'll hit the enter button. We get about 71.6 degrees. So the theta this theta here is about 71 or so degrees. What did I get? 71.6 degrees. Now that's a first quadrant, right? That's a first quadrant sort of angle. Or we could say then the theta then is 71.6 degrees north of east. So if you're looking east, which that's what the x-axis is, right? If you're looking east, you're going to shift your body 71.6 degrees north of east. And that will put you in line with the direction of the airplane. Okay, does that kind of make sense? Let's do another one. Okay, now that was velocity. We can also work then in what are called displacement vectors. Starting from my house, I walk 100 meters east and then walk 150 meters south. Okay, so there's my grid. So I'm going to put the two vectors. There's my 100. Okay, and then there's my 150. Okay, you create then a little box, and then we form the triangle here. So let me do this a little bit bigger here. We create this sort of box. This represents 100 east, and this represents 150 south. Okay, let me get a different color here. We'll connect then, we'll create then a little rectangle, and we'll connect then a line, an arrow from the origin to this intersection point. Now you see we've got two triangles here, but the triangle again we want, let me get a different color. The triangle again we want is this triangle, because that's tied into the grid, right? We always have our triangles tied into the grid, okay? And so this is the triangle we really want here. There's your theta here. This then would be 150. This is 100. So my Pythagorean theorem would be 100 squared plus 150 squared, and take the square root of all that stuff. Okay, you see that? Okay, so use your calculator again to find the Pythagorean theorem. I end up getting about 180. So again, what does that 180 mean? Well, I walked 100, I walked 150. Now I truly walked 250 meters, but that's a distance idea. Remember, displacement is where did I end versus where I started. I am now 180 meters away from where I started. That's displacement. Now, there's my angle here. So I could say, well, tangent of theta is 150 over 100. Okay, so again, how do you do that on your calculator? So I'm going to clear it. I'm going to hit second tangent 150 divided by 100. I get about 56.3 degrees. Let's just say around 56 degrees. Now, be real careful here. I can't say 56, right? I can't say I'm walking at an angle of 56. Why not? Well, 56 is in the first quadrant. I didn't go the first quadrant, okay? I went into the fourth quadrant here. So how could I express this angle correctly? Well, here's your angle. So you could say I'm 56 degrees. I'm 56 degrees south of east. That would be one way of expressing the angle. Or you could set this up truly as a fourth quadrant angle. You could say, well, 360 degrees minus 56. Okay, you could put that in your calculator. You get 304. That would be okay, right? Because a fourth quadrant angle is between 270 and 360, right? And 304 would truly be a correct way of expressing the angle. So we could express it as 56 degrees south of east, or we could say we're 304 degrees. Any which way, I walked 180, I'm at actually 180 meters away from where I started at an angle of 304 degrees or 56 degrees east of south of east. So we need really both parts, right? This is a vector. We need the amount, or called the magnitude, and then we need a direction, an angle. Talk to you later, kids. Bye.